Hi, I'm Shanawaz. In this lecture, we'll discuss the equivalence and equivalent categories. But before that, we'll first define when do we say two categories are isomorphic. So we have this definition. So let us consider two categories. So let A and B be two categories. Then a functor, say F, from category A to category B is called an isomorphism. If there is another functor, say G, from category B to category A, such that if we compose G with F, we get the identity functor on the category A, and if we compose F with G, we get the identity functor on the category B. Now this identity functor on A is actually a functor which takes each object to itself and each morphism to itself. So if this F is an isomorphism, then A and B are said to be isomorphic. So if this F is an isomorphism, then the category A and the category B are isomorphic. Now one should keep in mind that the isomorphic categories are considered as being essentially the same. Now there is a slightly weaker and more flexible notion of this essential sameness, and that is what we call the equivalence. So we'll first define what do we mean by equivalence and equivalence, and this is the definition of equivalence. So let say A and B be two categories, and say F from category A to category B be a functor. So then F is called an equivalence. Then F is called an equivalence if, so we have two items. The first item is that this functor F has to be full and faithful. So F is full and faithful, which means when we restrict this F to the home set of A, I mean, when we restrict this F to home set of A and home set of B, we get we have actually an injective as well as subjective map. And second is that this F is isomorphic dense, which means so F is isomorphic dense. So in the sense that if we choose any object to say B here, we get an object A in A such that F of A is isomorphic to B. So if B is an object in category B, then there exists an object, say A in category A, such that the object FA is isomorphic to B. then we call this Fn equivalence, and the categories A and B are called equivalent. So, so if this F from category A to category B is an equivalence, then the category A and category B are equivalent. So this notion of equivalence is slightly weaker and more flexible than being isomorphic. Now let us give some example. So this is the example of two equivalent categories. So let us consider the category mat. So let mat be the category the category with objects all natural numbers. So the objects in this category mat are all natural numbers. So with objects all natural numbers. Uh, and for which, so if we consider the morphism set between the object m and n, where m and n are natural numbers, so this is the set of all m by n matrices. M by n matrices. So one should note here the identity on object n is the identity morphism on an object n is actually the identity matrix. So the identity 1 sub n on an object n in the category mat is the identity matrix. I n of order n. The composition of morphism is defined like this. So the composition, so if we take two morphisms, say the composition of morphisms, say A, so A is a morphism, so this, suppose A is a morphism from object M to N, and B is a morphism from object N to R, suppose. So then we can have the composition. I mean, we can define the composition. So this is defined as, so we define B composition A, because B is a map from M to N and B is a map from M to R. So this is the composite map B composite A. So this is actually defined as A dot B, where this dot is the product of matrices, because we know each morphism is actually a matrix. So where B dot A denotes the matrix multiplication. Now we claim that this category mat is equivalent to the category of all finite dimensional vector spaces. So the category mat is equivalent to the category VC vec of F, where F stands for finite dimension. So this is the category of all finite dimensional vector spaces. So one should note here these two categories are not isomorphic. So consider so how are they are equivalent. So to prove this they are equivalent, we have to exhibit an equivalence. Now consider a functor, say f, from the category mat to the category vec f. So what it does, this functor takes an object n here and it maps it to r to the n, where r to the n is a vector space of dimension n over r. So this takes this object n to r. Now what it does with the morphisms. So and to each morphism, uh, to each morphism. So one should note here the morphisms here are the matrices. So to each morphism, which is an m by n matrix, to each morphism, say A, where A is an m by n matrix. So this is in the morphism in the category mat. So this functor carries this morphism to a linear map from Rm to Rn. So, so, so the linear, so, so there corresponds a linear map from Rm to Rn. So that this linear map assigns, so that assigns each say m tuple, say x1 up to xm, which is in Rm. So to each m tuple in Rm, and this assigns the 1 cross n matrix. So this matrix is given like this. So we have this 1 cross m matrix multiplied by the matrix A, which is of order m cross n. So the resultant matrix will be the 1 cross m matrix. So that 1 cross n matrix can be identified as an n tuple in Rn. So which can be considered as an n tuple in Rn. Now we have the following result. So this is a proposition. So it says that if A and B are two categories, and say this F be an equivalence from category A to B. So this is an equivalence. So be an equivalence. Then we have to prove there exists an equivalence. Say G from category B to A. So this result states that whenever we have an equivalence from category A to B, there is always an equivalence from B to A. So this is what we have to prove. So let us prove this. So let say this F be an equivalence from category A to category B. So let us consider some object, say A in A. So let first of all let us suppose that G from B to A be a map that carries objects to objects and morphisms to morphisms. And this G is such that and for each object, I mean, and for each object, let us take an object B in B. Now one should keep in mind that uh, F being an equivalence means that so F from A to B is an equivalence. So that means if we choose any object B in B, then there is an object A in A such that F of A is isomorphic to B. I mean, there is some isomorphism from FA to FB. And for each object B, choose an object, so GB. So one should note that GB is an object in A and an isomorphism. So, so that means we chose an object B in B, knowing that this F from A to B is an equivalence. So we have object B here and we have object GB here. So F being an isomorphism means, an equivalence means F of G of B is isomorphic to B. So that means there is some isomorphism which we denote by epsilon sub B. And for each GB in B and an isomorphism, say epsilon B from F of G of B to B. Now we claim that this G is a functor. Now to prove G is a functor, we have to first prove it preserves the identities and the so first of all we'll prove F preserves the identities. Now one should keep in mind, since F is an equivalence means F is full and faithful. So since F is full and faithful, uh, then for each morphism, Let us suppose G between the object is B and say B prime. So this is a morphism in the category B. There exists a unique morphism, say GG, from object B, sorry, GB to GB prime. So this is in A. So note that GG is a morphism in A because G is morphism in B. So G carries the morphisms of B to the morphisms of A. So GG is a morphism. And also note that B and B prime are objects in B. So GB and GB prime are both objects in A. So this F being full and faithful. So faithfulness implies that uh, faithfulness implies the uniqueness, and the fullness implies the existence. So using full and faithfulness, we claim that there is a unique morphism, uh, GG from GB to GB prime in A. Now, what is special about this? So this is with, if we look at f of G, we get, now since epsilon B is an isomorphism, we get this is epsilon B inverse composite with G composite with epsilon B prime inverse and epsilon B. So this is actually uh, a map between a morphism between the object f of G of B to f of G of B prime. So this comes from the fact that, so I want to note here, note that the diagram, so if we look at this diagram, so first of all we have uh, a morphism GG between the objects G of B and G of B prime. So this is the morphism G of G. Now we know F is an equivalence, so it carries objects to objects. This is F of G of B prime, and this morphism is mapped to F of G of G. Also note that from F of GB to B, we have this morphism. So epsilon B is a morphism from F of G of B to B. This is epsilon B. Similarly, we have a morphism here, epsilon B prime from F of G of B prime to B prime. And between B and B prime, we have the morphism G. So going from F of G of B to F of G of B prime, we first go via this path, followed by G, followed by this path. Now, since epsilon B prime is an isomorphism, so it is inverse, which is given as F of B prime inverse, which is a morphism from B prime to F of G of B prime. So one should note here, so F of G, G. So from this commutative diagram, and let us call this star. So one should note here, this diagram commutes, which means F of G is same as first go via the path epsilon B followed by G, then followed by epsilon B prime inverse. So this is what we wrote here. So this diagram commutes. Since this G of G is unique. Since G of G from B to B prime is unique. Now, what we want to prove, actually, we want to prove that G is a functor. For that, we have to prove first that G preserves identities. Now, to prove G preserves identities, we consider the following commutative diagram. Now, consider the commutative diagram. So, we go from f of G of B to f of G of B, and this is the morphism f of G of identity on B, because between B and B we had the map identity on B. Now from f of G of B to B we had the isomorphism epsilon sub B, and from here to here we had the isomorphism epsilon B, and between B and B we had isomorphism uh, we had the identity map I sub B. So we had to prove actually G preserves identities, i.e. we had to prove G of, so we had to prove G of 1 sub B is same as 1 sub G of B. This is what we had to prove. So now, now we have, so we have, so if we look at f of G of 1 sub B, so then by definition it is the map. First you go via epsilon B followed by 1 sub B followed by epsilon B inverse. I mean, you first go via this map, then via this map, then this map, which is epsilon B inverse. So this is same as, now if we look at, if you look at one sub B composed with epsilon B, that is same as epsilon B. So we get, so this is inverse here. So this is same as epsilon B composed with epsilon B, epsilon B inverse composed with epsilon B, because 1 sub B composed with epsilon B is same as epsilon B. Now this is same as identity on the object B. But since, uh, if you look at this object, so this is an object in A, and the map F is a functor. So this being a functor, we have, since we know a functor preserves the identity, so we know that F carries the identity on this object, which is the 1 sub B. So it carries it to the object 1 sub F of G of B. But if you look at this, 1 sub G of B is isomorphic to B via this isomorphism. So you can identify this as the identity on B. So using these two expressions, we come up with the argument. So this gives f of G of 1 sub B is same as f of 1 of G of B. But one should keep in mind that f is faithful. I mean, f is injective on home set. So that means if f of something is f of something, then that something is equal to the something. So since f is faithful, so G sub 1 of B, I mean the G of 1 sub B. So G carries this identity to 1 sub G of B. So this proves that G preserves the uh, identities. Now to prove G is a functor, it remains to prove G preserves the uh, so we have to prove now uh, if we have two morphisms say H and G, then G composite H of G is same as G composite H composite G composite G of G. So that is F preserves G preserves the composition. So this is what now we are going to prove. So let G be a morphism, or let us call this H. Let H be a morphism from B prime to B double prime. So be a morphism. So this is a morphism in category B. So if this is the case, then we have the following commutative diagram. Then we have the following commutative diagram. So we have the object f of g of b and a morphism to f of g of b prime, then another functor, uh, another morphism to the object f of g of b double prime. So for this object we have a morphism epsilon sub b to the object b, and here we have a morphism epsilon sub b prime to the object b prime, and here we have the morphism epsilon sub b double prime to the object b double prime, and here this is the map G, this is the map H. So one should keep in mind that this is a map G, sorry, H composite G, and this is a map. So this is the map. So we forgot here to write the morphisms. So this is the morphism f of G of G. This is the morphism f of G of H. So this is the composite morphism f of G of H composite f of G of G. So this is the commutative diagram. Now, if that is the case, this gives, so this gives, so if you take this morphism from this object to this object, it is same as first go via this map, epsilon b, then followed by this map and this map, which is epsilon b double prime inverse. So this gives uh, f of g of h composite f of g of g. So this is same as first go via this map epsilon b followed by this map, which is h composite g followed by this map, which is epsilon b double prime inverse. Now this is same as, since f is a functor, this would imply f of g of h composite g of g is same as epsilon b double prime inverse composite h composite g composite epsilon b. Now let us consider the morphism. So now consider the morphism say edge composer G from object B to B double prime. Now since F is full and faithful, since this functor F is full and faithful, then for this morphism edge composer G, there exists a unique morphism which is G of edge composer G. So this is the morphism from object G of B to G of B double prime. Such that this is the morphism in A with, such that the diagram commutes. So that is, we have F of G of B, we have the object F of G of B double prime, and this is the morphism F of G of edge composer G. This is the isomorphism epsilon B to B. This is the isomorphism epsilon B double prime to B double prime, and this is the morphism edge composer G. So since this diagram commutes, this would imply this morphism is same as first to go via this map, followed by this map, and followed by this map, which is epsilon B double prime inverse. So that is F of G of edge composer G is same as first to go via epsilon B, followed by the map edge composer G, followed by map epsilon B double prime inverse. So if you look at this expression, if we look at this expression and this expression, both expressions have same right hand side, so this would imply the left hand sides are equal. So this gives F of G of edge composer G is same as, so what is the left hand side here? So it is like this. So this is same as F of G of edge composer G of G. Again, F being faithful implies F is injective, and hence, this gives, so this implies G of edge composer G is same as G of edge composer G of G. Again, the reason is that F is faithful. So this proves that this G is a functor. So one should note here that we had to prove G is an equivalence. So we are done this far. We have proved G is a functor. Now it remains to prove G is full, faithful, and the isomorphism terms. So first we prove that G is full. So consider any morphism. So we have to prove this G is surjective and restricted to the home set. So consider, one should note here, G is a morphism functor from the category B to category A. So we have to G is full. We have to prove G is surjective and restricted to home set. So we are going to take some morphism in category A. We will show that, and that morphism has a pre-image under G in category B. So consider any morphism, say F from the object, say GB, one should know that GB is an object in A, and GB prime is also an object in A, while B and B prime, sorry, where B and B prime are objects in category B. So if this is the case, then we have so so if we look at the diagram, so clearly the diagram which is given like this, so we have f of g of b to f of g of b. So if we look at this map, so between GB and GB we have found morphism F, and when we evaluate F at F we get this morphism F of F. So this is the isomorphism epsilon sub B to the object B, and it is isomorphic to B, so this is B prime here, via the isomorphism B prime. Now we have to evaluate this map. I mean, this map is unique, we know that, because F is given to be an equivalence, which is full as well as faithful. So now to exhibit this map, so I mean, going from B to B prime is same as first to go via this map, which is epsilon B inverse, then follow this map, and finally this map. So first of all we have to follow this map. So this is epsilon sub B inverse followed by f sub f of f followed by this map epsilon B prime. So this is unique, that is why this map is equal to this map. So we write, so write G to be equal epsilon B prime composite f of f composite epsilon B inverse. So this is a morphism from B to B prime. So then if we compose G with epsilon B, so when we multiply with epsilon B inverse, we get epsilon B prime composite f of f. Now if we look at the commutative diagram in star, so if we look at this diagram, I mean the commutative diagram in star, we know that uh, epsilon B composite G, so sorry, this is G composite epsilon B, so this is G composite epsilon B, this is same as epsilon B prime composite f of G. So also uh, from star, I mean from the commutative diagram in star, we have, so we have G composite epsilon B is same as epsilon b prime composite f of g of g, f of g of g. So thus, if we look at these two expressions, this expression and this expression, so they both have same left hand side. So thus, right hand sides are equal. I mean, epsilon b prime composite f of f is same as um, epsilon b prime composite f of g. Now epsilon b prime being an isomorphism, so we can compose from right this expression with epsilon b prime inverse. So since epsilon b prime is an isomorphism, we get this expression to be equal to this expression. So we get f of g is same as f of f. Again, using the faithfulness of f, uh, so this further gives g of g is f. The reason is that f is injective when restricted to morphisms. I mean, f is faithful. So we started with some object, some morphism f in the category A, and we ended up by showing that there is a morphism G in B, such that, so this is the morphism B. So we started with F. We chose F and F a morphism in A, and we showed that there is a morphism G in G, such that G of G is F. So that means this G is full. Now we prove G is faithful. I.e., we have to show that G is injective when restricted to home sets. So let uh, G1 and G2 be two morphisms from B and B prime in the category B. B morphisms in category B such that G of G1 is same as G of G2. So we have to show G1 is equal to G2. Again, we are going to use the diagram in star. So the diagram in star yields, so if we look at G1, so one should, so let us first draw the diagram here. So we have f of G of B to f of G of B prime. So this is the morphism f of G of G. So, and here we have the map epsilon B to B, and we have the isomorphism epsilon B prime to B prime, and between B and B prime we have two morphisms. One is G1, other is G2. So we know f of G1 is same as f of G2 because f is injective. So this is same, this is G1 here, the same as f of G2, like this. So this G1 is same as, so if we first look at this G1 is same as, first use epsilon b. So G1 is same as first go via epsilon b inverse, then via this map, then via this map. So this G1 is same as first to go via epsilon b inverse followed by, so like this. So this is epsilon b inverse followed by f of g1 followed by epsilon b prime. Now f being injective, so if they are equal, then f of g1 is same as f of g2 because f is injective. So two same points have same image. So that means we can replace this f of gg1 with f of gg2. This is epsilon b prime composite with f of gg2 composite with epsilon b inverse. But that is same as the map g2 because g2 is same as first go via epsilon b inverse, then via f of gg2, then via f of b prime. So this is same as g2. So this proves the map, this proves that G is full. Now finally we have to show that G is isomorphic dense, which means that we have to prove, since G is a morphism from B to A, G is a functor from B to A, we have to prove that for any object in category A, say if we have object star here, in category A, there is some object, say pound here, such that G of pound and star are isomorphic. So this is what we have to prove. I mean, G is isomorphic dense. So G is isomorphic dense. So let A, sorry, let A be any object in A. Then f of A is clearly an object in B, and hence if we look at the object f of g of f of A, this is small a here, so then f of A and f of g of f of A are both objects in A. Now we start with some object, so this is the object in A. When we take the f image of this object in A, we get an object in B. So then f of A and hence this object are both objects in category B. Now let us consider the isomorphism. So consider the isomorphism, say epsilon sub f of A. So that means this is an isomorphism from f of g of f of A to f of A. To f of A. So this is the morphism. Now we know that if f is, so we proved in last lecture that if f is a functor from category A to category B, and if this f is full and faithful, then for each morphism, say G in category B, there is a morphism in category F such that G of f is G. So we are going to use that result here. So So this is a morphism in category B. Now, since F is full and faithful, so this F is a functor from category A to category B, and here we have this morphism epsilon sub f of a, which is isomorphism as well. So then by that result, which we proved in last lecture, there is some morphism in category A whose F image is same as this isomorphism. So there exists a unique, I mean, an isomorphism, say H from G of, so from this object to A, from G of, so from G of f of A to A, such that the F image of this isomorphism is same as this isomorphism. Now, why this is an isomorphism? Because F is a functor. It preserves isomorphism. It carries isomorphism to isomorphism. So if epsilon f of A is an isomorphism, then this morphism is also an isomorphism. That is why we wrote here isomorphism. So the reason is that since functors preserve isomorphism. So since so H is an isomorphism. So if H is an isomorphism, that means this object and this object, they are isomorphic. So thus G of f of A and is isomorphic to A. So this is what uh, we had to prove. So actually what we proved here, so G was a morphism from B to A. We had to prove for each object in category A, which is, so this is category A here. For each object in category A, we proved there is an object f of A in category B whose G image is isomorphic to A. So that means this functor G is also isomorphic dense. So this proves finally that G is also an equivalence.